Okay, so to some of you, this is the second time I'm introducing myself. But yes, I'm explaining ICS to a fool of a toque. So it's a high-level description of ICS, which I'm researching. And it's a halfling ramble because I go by halfling online. So I'm halfling, but I'm also Jenny Highfield. So welcome. I'm a software engineering teacher at Cardiff University. I came in as a teaching associate and then started working as a teacher where I lead a module called web development at the National Software Academy. But I'm also a part-time second-year PhD candidate. So we have 5 to 7 year part-time PhDs, and I'm researching this for my PhD. So industrial cybersecurity, that's my area. And lately, I know that I'm still researching and working in tech. Spend a lot more time outside these days. I worked in the industry as a software engineer for a long while, but I think I much prefer spending time outside. So we have a problem. So it's possible to hack things, and we rely on those things. So from the watch on your wrist, to the thermostat in your home, to the machine that squeezes your orange juice, because some of them are IoT now, and the app that you use to buy your train tickets, the card that takes your payments. There's a lot more than that though. So I want you to imagine something, and this is just a bit of an exercise because when I close my eyes, I can't see a red apple. And I didn't realize that some people can close their eyes and see a red apple. So for some people, we need to demonstrate things a bit better when we explain why something's catastrophic. Some people can close their eyes and see two trains colliding together. That must be a horrible thing to be able to envision. For me, I'd only be able to envision that if I was just about to fall asleep. Like, that's when that area of my mind comes alive. But for other people, they could imagine that at any time. And my laptop's just told me that it's now low battery, even though I charged it fully this morning. So I better put that on charge. Actually, there's the charger here. Should be fine. There we go. Problem solved. Okay. So yeah, I don't want you to imagine the red apple though. I want you to imagine, first of all, the thermostat in your house. So what happens if someone hacks into that? Right? So you set it to 20 degrees. If it goes above 20, it'll turn off. If it goes below 20, it'll turn on. There's another slide on that later, but someone hacks into that. It could get really hot in your house or really cold, but it's not the end of the world. And then what about medical devices though? Last year I had a master's degree student for their dissertation hack BLE devices, Bluetooth Low Energy. And she was hacking an insulin pump. And she managed to do it. That's terrifying. Yes, it was isolated, it wasn't being used. But she managed to hack an insulin pump. And if she can do that to one that isn't being used, then it can be done to one that is being used. And I know if you go to any of the B-Sides conferences, at the beginning they will tell you, don't hack medical devices, don't go around hacking devices. And they actually have to say that. And that's crazy because if you know how to hack things, you know how to hack really important things as well as really stupid things. So what about traffic lights, train signaling systems? Make two trains go into each other. What about a nuclear reactor? Same premise as a thermostat. When things get too hot, it gets cooled down. Control rods are added, very simply put. But it's the same premise. You hack into it, you make the sensors think that the temperature is different to what it is. So these are the pillars upholding society. So these are critical national infrastructure as defined by the NCSC in the UK. So we've got chemicals, civil nuclear, communications, defence, emergency services, energy, finance, food, government, health, space, transport, water, and there is a 14th now. But we're completely reliant on all of these. And these all didn't used to be reliant on technology. They all didn't all used to be reliant on each other. They're all linked. Chemicals go by freight. Water, how does water get around? Probably freight as well. But the water systems, how does water get from the water treatment plant to your tap? Like there are attacks that are known on that, like the Maroochy-Shire sewage spill that happened in Australia. So the 14th sector was added last year, and it's data centres. So they're now critical to society's function, or they've always been critical to society's function, and we've just added them in. Because how many of the other sectors rely on data centres? What about finance? So it was announced by the UK government as of the 12th of September 2024 that it is now classed as CNI. And on a side note, I currently have a final year project student creating a SCADA testbed from Arduinos and Raspberry Pi, so a very basic one. And I said you could choose any sector of CNI, and he chose data centers. And I'm very interested to see how he manages that, and it's going pretty well. But that's the one area of CNI that I couldn't really vision how you would properly show that in a testbed, because there are cooling systems, but there's also a lot of data being stored, and how do you replicate that? So he's currently in week 5 of week 12, so I can't wait to see what he comes up with. But the plan looks good. It's just it's not the sector I would have chosen, because it's probably the most difficult sector to actually visualize and show in a testbed realistically. So critical national infrastructure. They are the national assets that are essential to the functioning of society, so such as those associated with the energy supply, water supply, transportation, health, and communications. And that's the quote from the NCSC. So any of the 14 sectors are classed as critical for maintaining life as we know it. Cybersecurity demonstrators. These don't have to be technical. They just have to show that something's happening. So they can be shiny things to convince C-suite executives in companies, or the people at the top who don't really understand the technicalities behind the issues. But they want to see that when you press this button, this blows up. And you show them that, they're like, yes, we'll throw money at that. So that's the purpose of these. It isn't to technically show what's going on, but to show what's going on a high level. So C-suites like flashy things. Something happens, boom. So they're chaotic good, because there can be a lot of money spent on something quite flashy and non-technical, but it can also get big companies to spend a lot of money, I'd hope a lot of money, on security and actually securing their assets. So it's not always useful for actual cybersecurity research, but you can have some demonstrators that also have working components such as PLCs under the hood, and they can be a hybrid demonstrator and testbed. So here's an example that the Cyber Innovation Hub have. So the Cyber Innovation Hub are a joint-led research group between USW and Cardiff University. So they are planning on spinning out 4 things like this. But this is one of the demonstrators that they have built, actually partially designed by Alex in the front row, who's one of their cybersecurity research engineers. There is a video of this too that I can show anyone who wants to come find me after. But these lines are all being projected from top down, and it cycles through different almost stories that show cascading effects of when an attack happens on this, it goes from this sector of CNI, and then it cascades to this one, and then cascades to this one. And you can see, I think the lines are energy moving on this, or different like water and electricity, different utilities moving around. But that's just one example of a demonstrator. So industrial control systems, what are they? So going back to the thermostat example, it's as simple as temperature is set to a value. If temperature is equal to the value or more than the value, the heater turns off. If temperature is less than the value, the heater is on. So that uses something called a control loop. And this is actually a diagram that I made in LaTeX for my write-up, and I'm really proud of it. So this is a process control loop. The sensors, I just remembered the cameras by there. The sensors pick up signal, the actuators make the changes based on the sensors. And then if I go back, so this, a basic version of this is what I have my dissertation, my final year project student building as a mini test bed with Arduinos and PLCs, no, Arduinos and Raspberry Pis, especially being you can put open PLC, which turns OpenPLC on a Raspberry Pi, which would allow you to use it as a PLC in one of these systems, because PLCs are very expensive to get your hands on, and this means that you can replicate it using a small device. And if any of you have Raspberry Pis, Arduinos at home, maybe give this a go, it can be quite fun. But yeah, the sensors pick up a signal, then the actuators make the changes according to those signals. So there's a lot of buzzwords here. You'll hear a lot of different things thrown around. So operational technology, what is it? It's the umbrella term for all of these industrial systems, essentially something that takes in signals and makes changes according to those signals. So operational technology, industrial control systems. Within there, we have SCADA systems, supervisory control, and data acquisition systems, distributed control systems as well as industrial IoT. So all of the IoT devices that have been brought into these systems more recently that allow us to track changes remotely rather than controlling them in the same room as where all your systems are. So there are 4 generations of industrial systems: the monolithic systems, distributed, networked, and industrial IoT. So the first generation, monolithic. And if you're thinking of like a big monolith like Stonehenge, yes, you're thinking of the big industrial systems, the mainframes that would be behind things like nuclear reactors. So these were built in the 1960s and 1970s. And if you're thinking of security, what would security been like in the 1960s and 1970s? Well, it was, you know, it was pre-internet, so they were air-gapped by design. So they were controlled locally. You wouldn't be controlling them somewhere else because pre-internet. So second generation is distributed. These are 1980s. So a bit more connection, a bit smaller, more powerful mainframes. And you access it through a local area network. So you might be controlling it in a separate room rather than on the device you're actually using. So from monolithic to distributed, there's been an increase in interoperability between the systems. So the third generation is networked. So these were built in the 1980s with increased network capacity and interoperability compared to distributed. And the network protocols and there were network protocols that were defined during the 1980s, which they weren't for the previous 2. That meant that there was more standardization between systems that were being built. So rather than one company make this system, one company make this system, and a SCADA engineer going from one to the other would have to completely relearn all the equipment. It means that no, they actually can apply the same protocols from one to the other. So the 4th generation, industrial IoT. So these are 2000s onward. And I imagine a lot of the students in the room here are born 2000 onwards. So these are your generation. So these are linked through an API to the HMIs, so human machine interfaces, such as web applications. So say there's a control system on the other side of the world that I somehow have access to. I can literally control it from my laptop, which is a crazy idea. Because one thing about these is that these 4 systems aren't completely isolated from one another. Each system has had the ones that came after it added into them. So the first generation, a lot of the new equipment coming out for them now have network capabilities added into them with the same serial number. So if you've looked into OT security before, this is one of the first issues that a lot of people learn about. The same item bought again with the same serial number might arrive with network capabilities with default passwords. If it's got the same serial number, why is it not the same? So another thing is that IoT devices are literally being added into the original systems. So the systems built by, secured by air-gap originally have had these new devices with new security vulnerabilities, because IoT is a massive area of research at the moment because these devices are being built, but they're not necessarily secure. And the vulnerabilities from them are being fed into even the monolithic systems built in the 1960s. So there's a massive problem there. So I'm going to be going through the Purdue model with you. I am using information from the SANS Introduction to ICS Security Part 2 workshop, and not workshop, but their information they have available online because it's just the best way of explaining it in my opinion. So there are 6 levels to the Purdue model. And even though I'm a software engineer, it still catches me out that it begins from 0. So I'll go through each with the information from SANS. So you have level 0 to level 5, with 4 of them being OT and 2 of them being IT, with a DMZ in the middle. So the Purdue model was created in 1980s by Theodore J. Williams at the Purdue University. So let's go through it. Level 0, field devices. So these are sensors and actuators. So sensors detect the change, sensors detect the change in the variable that's being monitored. Actuators make a change according to what's being sensed. So sensors and actuators for cell line process. Sorry, my mind's, yeah. So sensors and actuators for the cell line process or DCS solution, often combined with level 1. So these are basic sensors and actuators. Smart sensors, actuators speak in field bus protocols, intelligent electronic devices, and industrial Internet of Things devices. So could be a sensor that's in an IoT device and that's being connected in through Wi-Fi, for example. And these are where the communication gateways are. So level 1, so these are devices and systems to provide automated control of processes, cell line or DCS solution. So modern ICS solutions often combine 1 and 0 together. So these include PLCs, so programmable logic controllers. Again, if you want to try out using a PLC, you can put OpenPLC on a Raspberry Pi. Control processors, programmable relays, remote terminal units, so these are very similar to PLCs, and process-specific microcontrollers. So local supervisory, so monitoring and supervisory control for a single process, cell line or distributed control system solution, isolate processes from one another, grouping by function, type or risk. So these include HMIs, so the web application that might be connected to the, the web application that might be connected to the system that it's controlled from. Alarm servers, process analytic systems, historians, and this would be the control room. So site-wide supervisory, monitoring, supervisory and operational support for a state or region. These would be management servers, human-machine interfaces again, alarm servers, analytic systems and historians if scoped for an entire site or region. Then we'd have the demilitarized zone for the IT-OT boundary. So we've just talked about the OT, so operational technology, and now the last two layers of the Purdue model are IT. So these would be business networks. So the IT networks for business users at local sites, connectivity to enterprise-wide area networks, and possibly local internet access. So direct internet access should not be extended below this level. So business workstations, local file and print servers, local phone systems, enterprise active directory replicas. So that would be the business network side, and then you've got the enterprise networks. So corporate level services supporting individual businesses, units, and users. These systems are usually located in corporate data centers. So servers that provide enterprise active directory, internal email, customer relationship management systems, human resources systems, document management systems, and backup solutions. Is there another one? Yes, enterprise security operation centers. So these should all be very, very separate from the OT. That DMZ is really important. Can you see how you don't want these anywhere near the OT? So I know these last few are me reading off the slides bit, but I think getting this information right is quite important. So they're the only ones where I'm reading off like that and it's not my content, but I'd say the SANS websites are really good for that. Okay, so how do you program PLCs? So this is something that took me a while to get my head around because I was thinking really, really technical, but ladder logic was actually built for engineers to use, and it's actually quite similar to Scratch. So this example on the board, the image is just for aesthetic reasons. So I realize it's actually not the best one, but it's essentially where you have the my mind's gone blank. Where you have the diagram, it would be read left to right, line by line. And it's like Scratch in that you can click what you want on each level, and then that's how it's read. It's one of the things, if you want to learn about it, YouTube's probably the best place to be. And you learn by watching someone else doing it, or you learn by doing it. It's something that having someone explain at the front like this with me explaining it to you, it's not the best. But if I was showing you how to do it on a computer, which might be a good idea for me adding that in the future, it'd make a lot more sense. So if you want to learn about this, YouTube, watch someone else do it, or give it a go yourself using OpenPLC. So ladder logic is one of the main languages for programming PLCs. And yes, it looks like a circuit diagram. That's the phrase that left my head because I'm in front of a massive room of people and I couldn't think. So yeah, circuit diagram. So when you can see the power flowing across, running one line at a time. So these are one of the IEC standard languages. However, there are ways to program these, I believe in Python now as well. So it started off as a way for engineers to quickly program something without needing to know a really low-level language. But there are new methods of programming these now. So industrial-specific network protocols. Regular network protocols run on all of these systems, but these are what makes a network operational technology. And this would be a talk for another time. This is something that I could talk a lot on. But these are the ones that if you were, say, looking through a network on Wireshark or looking through a data set, a OT-specific data set, these are what you would find that would make it different from a regular IT network. So if you think of the Purdue model, the first 4 layers, they're the ones where you would expect to see these. The last 2 layers, you would not expect to see these at all. So you've got Modbus, CAN bus, Profibus, EtherCAT, CIP, CNX, AMQP, and BACnet. And I will talk about a couple of them a bit more when I talk about the testbeds and demonstrators that I've been involved with. So I talk about the cyber physical system testbeds, and these are some that I've either used for training or that I have access to through work. So I was lucky enough to do a Hactronics course. So this is done by Joe and Owace from Bristol Uni, and they brought in like PLCs in a box, and we ran scripts on that, which was linked to factory IO, and using Python managed to make a conveyor belt go the other way and cause boxes to fly everywhere, and it was really cool. So yep, sorry, I should have been clicking as I was going. Yeah, so we also exploited a vulnerability in virtual network computing. So when you're controlling something remotely, like if you've ever had IT take control of your computer, that probably uses the remote buffer framework, remote buffer protocol. Yeah, that uses a remote buffer protocol, and that is what's underlying with VNC. So we exploited a vulnerability in VNC that meant that we could connect into it. Yeah, so it's Professor Owace and Dr. Joe. So another course that came to university was a SANS ICS course. This was sourced for postgraduate students. So we use PLC and Open PLC. So in the image you can see on the left is an actual PLC, but we also had Open PLC running too. And so we used both for this course. So it was a full day course, and it was very American. It was very sales pitchy, but it was very good still. So it wasn't my cup of tea compared to the Hactronics one that was run by Bristol. I really loved that one. It was very up my street, but it was still a really good course. So this is one of the test beds that we have in Cardiff University. So it's an oil and gas rig. So it was built for Dr. Abu Mohammed's research by one of our technicians, David Savell, and he's an absolute genius. So Abu works for an oil and gas company in Nigeria, and he had this built to be as close to the spec of what they have over there as possible. And even though he's finished his PhD now, and he found a novel field flooding attack, I think he called it. He found a novel attack against the PLCs on this, and he managed to replicate it across 3 test beds, and that was his PhD. But we still have this for research at the university, which is really cool. So it's in our cyber lab, built by Dave. Dave is awesome. And if you want to look at Abu's research, he actually created an OT data set from this, which is available on GitHub if you wanted a data set to play with, to look for if you're looking into attacks on OT devices, because his data set shows his field flooding attack working. Another thing we have is a smart city with a Hornby Railway. So it's one of my favorites because I love model trains. And effectively, there is an actual PLC here, so it is a hybrid. So it is a demonstrator and a test bed, but the PLC only sends on-off signals, and very basic ones at that for this. So the train is either on or off, and then the lights for all of the city are either on and off. So there are 2 PLCs, and that's all they're being used for, is on and off in both scenarios. So it would be really cool, and I do want to work on this to make it so that it does more, so that maybe there's a variable speed on the train, which is really difficult and really expensive to have a model train have variable speeds. But I know that the team at Cardiff would like it so that the different buildings have different lights turn on at different times. So it has a Schneider Electric PLC controlling the train, and a Siemens S7 PLC controlling the smart city. And there are books that literally talk you through hacking a Siemens S7 PLC. So if anyone wants any advice on any books to read, just come ask me afterwards. So it's a demonstrator, but it's also a testbed, like I said, and it's vulnerable to the field flooding attack that Abu also did on the oil and gas testbed. So we also have a car simulator, and this is just really cool to just, I guess, drive on when I'm bored. But yeah, that's not what it's built for. So if any of you have been to any of the B-sides and know David Rogers, so he has some really cool bigger versions of these that he brings to B-sides for people to come have a go on. So it simulates attacks while driving. So if you get a student to sit on it and drive, which is quite funny because some of them don't drive, so you have to actually teach them how to drive and how to use the gear stick and stuff. But you can press buttons that will cut the brake, cut the clutch, cut the accelerator while you're driving, so you can see what it would be like if an attack happened on a car, like the digitized cars these days, what would happen. And it's quite scary. So it uses OpenCAN, which is an open source version of CAN bus. So CAN bus is the protocol used for connection within the connections within a car. And this is also both a demonstrator and a testbed. So then digital twins and simulations. So these are connected and standalone simulations. So the difference would be that digital twins can have a bidirectional connection or one way. And digital twins, ideally, not ideally, the definition of digital twins from the NCSE means that you have a digital replica of your system, but of an actual CNI. So what we're building, when we're creating a digital twin of a test bed, that's not really a digital twin, and I haven't figured out what people call that yet, or what I should call that yet, because that's being built as well and being called a digital twin. But a digital twin has to have a one or two-way connection to the thing being twinned, and that should be an actual piece of ICS. So the one-way connection would be from the industrial control system to the twin so that it can mirror it. But then the two-way connection would mean that that then sends data back to the industrial control system as well, which is obviously more security risks there. So simulations are then standalone and not connected to the cyber physical systems. So there's no connection at all. You find out as much as you can about the system to be simulated, and then you simulate it. So the definitions differ from paper to paper. This is something, if you're reading papers in this area, digital twin will be used for simulations, and then virtual twin will be used for something else. So there's a lot of different definitions. So what I will say is, if you're ever writing a paper on this, or a blog, or whatever you're writing, write down your definitions and where they've come from and who you agree with, so that people know when you're using these terms what you mean by them, because it's not clear from place to place what people mean by this. You can go to one event, and I know Alex went to an event the other week, and have 3 talks back to back where each person have used these terminologies in a different way, whereby if you give the definition up front, this is what I mean when I say this, it means there's not going to be any confusion there. So last year, we had a bunch of research assistants working with us, and they then did their final year projects linked to what that research was in. This was one of the dissertations that I oversaw, so it wasn't supervised by me, but it was supervised by my PhD supervisor at the time, so I was involved with it. So for the Cyber Innovation Hub, he was paid as a research assistant to build a smart house that shows utilities going in and out of the house. And He also created a waterway simulated contamination that he managed to name simulation of hydrological impact and treatment, I think. So if you figure out the acronym there, simulation of hydrological impact and treatment. And it took him a long while to come up with that, but he was very proud of himself for essentially calling it shit. But that was one of the simulations, and that links into another piece of work where another student was working on home assistant using IoT devices, and they managed to get an API working which was built by another student. They all merged it together where Home Assistant links to the API, which links to this. And if you turned a light on or off in this, or a light on and off on an IoT device, they would then turn on and off on there. So they had like a digital twin working between Unity and Home Assistant, and that was really cool. So Factory.io, this one's been mentioned earlier. So it's a simulation of a factory line, and it can connect to a physical or a virtual PLC. So it shows cascading effects visually. So if you think of each box that could be in here, each box could go to a different sector of CNI. You could have chemicals in one, you could have water bottles in the other, you could have, let's think of a random one. I don't know. Someone shout something out. What could you have in a box? Keyboards, yeah. Anything else?
Teddy bears.
So CNI is anything that stops society from functioning. So I think taking all the teddy bears away from kids, yeah, we might have a problem, yeah. Cyber ranges. Hands up if you've heard of a cyber range. Yeah? So cyber ranges are really cool. They allow you to simulate networks in a virtual topology. So not many of you use cyber ranges, but have you all used VirtualBox? Yeah. Big version of VirtualBox. Very powerful. You can have lots of network topologies and lots of VMs on there. You could have, so this one, we were told should be able to have 30 students using it at the same time. Was it 30? They said 200. Yeah, so we were told 250 VMs should be able to run on this. Not sure we got that high when we were stress testing it, but they're really cool, and they can be used for teaching. And it's a virtual sandbox for cyber attack research, like VirtualBox. And you can also plug in physical PLCs into this, and physical devices, or even a computer. You could have a workstation. So what you could do is you could have a test bed that plugs into this, has a network topology, and then connects to a machine that has a GPU with a simulation on it, and that could all be connected together. So these are really cool, and are kind of they're important for the middleman between your simulation and your test bed if you have something quite powerful. So industrial network vulnerabilities. So generic network protocols are used. So all generic vulnerabilities apply to these systems. So PLCs are vulnerable to DDoS, such as the field flooding man-in-the-middle attack that Abu found. So industrial protocols lack encrypted data streams. So we were looking at the car earlier. So CAN bus has an unencrypted data stream. And then industrial control systems use VNC, so virtual network computing, which uses unencrypted data streams as well, such as the RFB protocol. So the interconnectivity of the 14 sectors, they all cascade between each other. So nuclear relies on water, very obvious. Nuclear powers need to have a big water lake or reservoir near them for cooling. So water relies on transport, finance relies on data centers, emergency services rely on communication. Yeah, so there's probably a big map to be made there. They all rely on each other. You attack one, it will feed into all of the others. But how do you stop that? Big questions. So protecting ICS, and these are very, very, very high level. But it's a very active area of research. Don't breach the air gap unless absolutely necessary. Don't add an IoT device into a monolithic system without testing that the IoT device is actually secure first. I think it was obvious, but the SCADA engineers working on these systems are not security experts. Separation of IT and OT where possible. You don't want Active Directory to be anywhere near an OT network. Restrict access to critical systems to those trained. And train personnel and enforce security policies. And very obvious one, coming back to the one that everyone will know, Stuxnet, deactivate USB connections. So how is this relevant to me? So my PhD has changed a bit. I'm now looking at pedagogical approaches for ICS education. So my original topic trajectory didn't really excite me. I was looking at operational technology incident response, which is a really cool area. And I had a project in mind and I was going in a direction that I really liked, but at my 9-month review or at my last review, I would have had to pivot a bit into an area that didn't really excite me. And to get through a 7-year PhD, you have to be working on something that excites you. And I want to be building these kind of systems. I want to be building things. So I was thinking, how can I build something and still answer research questions? So I have had a pivot where I'm now looking at how can I build test beds, simulations, digital twins, and teach people about these using these hardware solutions and digital solutions, these assets. So that's now my PhD, and it does excite me because it means I get to build test beds, to actually get my hands dirty and build things, design them and build them. And then they can actually be used for cyber attack research, which I can still carry on with cyber attack research. But the kind of research that does excite me, rather than having to answer research questions that are definitely going to get me a PhD. And I also get to provide outreach, which is one of the things I really care about, because I was trying to do this on the side of my PhD anyway. I wanted to build these. I've got an idea in mind, but I need to make sure it actually answers the research question I'm trying to answer. But I want to build a piece of equipment that can be taken into schools and into colleges and even universities to teach about this, but on a smaller level and much more kind of starting from the ground up level. And I can provide more outreach and I can find more time for it, because since I started my PhD, I haven't really found much time for outreach at all. So, diolch yn fawr iawn. Thank you very much. Are there any questions? Go on.
Yeah, so I don't have much experience with OT at all. I was curious what a field flooding attack actually entails. Like, are we talking about trying to fault sensors physically, or is it a digital attack?
Oh, trying to think back to Abu's paper now where he describes it.
Or just more generally, rather than that specific one. Like when
it's the man.
Are the test beds representing physical faults that can occur in the environment, or sort of digital attacks?
Oh, it's a man in the. I hope this answers it. It's a man in the middle attack on the PLC. But yeah, it's DDoS on Modbus.
Okay, yeah.
Yeah, it's one of the areas where it's been done before on different things, but it's never been done on this before. So it is novel, but it has been. It's not been done on OT like that before. Yes, it's a digital attack. Yes. Yeah. Sorry. Yeah. Any other questions? So a lot of the systems that we rely on are decades old. I need to actually look into properly what's going on there to answer that correctly, but it's my assumption that the companies that have more money that are upgrading systems but not replacing everything, they are probably adding more IoT into their systems, and I hope they're security testing them before they do that. But then what worries me more is that I remember a discussion about 5 years ago, 5 years ago, 4 years ago, 4 years ago, I had a discussion at a conference in London with someone who owns a brewery actually up here in Scotland. And he was saying that he needs to upgrade his OT system behind how the brewery runs, but he was really struggling knowing how to upgrade it and patch it, because if you patch it, everything comes down, and with these systems, you don't want downtime. So I think smaller companies like that are probably the most worrying in adding things in that they might not understand. But he was asking all the right questions, so he was looking to talk to someone to get help with this. So I'm hope that they figured that out and they managed to upgrade their systems or choose not to. But I think IoT does come across as a quick fix. It's like, oh, I'll add that in and I'll just connect it by Wi-Fi. Can't really answer your question for definite, but it's an interesting talking point, definitely. No, yeah, of course. Any other questions? All good?